Hi, this is Wes Simpson with LearnIPVideo.com. I'm here today representing AIMS, Alliance for IP Media Solutions, and we're having a discussion about various topics involved with IP media. With me today is Jed Deame. Jed is an old friend of mine. Why don't you tell us a little bit about what you do and what your company's all about, Jed?
Yeah, hey Wes. So I'm Jed Deame. I'm the founder and CEO of NextEra Video. So what we do at NextEra Video is a variety of things, mostly which is providing solutions to help OEMs develop their own products. In particular, we do cores for SMPTE ST2110 and NMOS.
Ah, okay. So people buy your technology and incorporate it into their products?
Yeah, that's exactly right. They can get a jump start to building their own products, whether it be gateways or just IP enabling their current devices. We can give them all the tools they need to get their product to market very quickly.
So would end users ever be customers of yours, or is it pretty much always somebody who's going to take your technology and build it into something else?
Yeah, at this point, it's directly sold to OEMs to help them get their products out there.
Ah, cool, cool. Well, very good. So today we really wanted to talk a little bit about NMOS, the networked media open specifications. And for people who don't really understand that, why don't you just give us a real quick overview and the role that NMOS plays in the AIMS roadmap, Jed?
Sure, yeah, I'd love to. Really, NMOS is intended to be the layer of software that makes ST2110 systems work and communicate. So it's the control layer. So if you think of 2110 as the plumbing that really connects sources and receivers together in an IP world, NMOS is the control layer that orchestrates that. So I can walk through a couple slides here that kind of show an overview if you like.
That'd be great.
Okay, so really in an IP system, what we're doing is we're changing this center portion here, which historically would have been a SDI cross-point based router, and we're replacing it with an IP switch or an IP switch subsystem. So of course, all the devices, all the sources will need to be IP enabled, and all the destinations and of course the video switch will need to be IP enabled. But then that kind of begs the question, well, how do I actually control this? And that's really what's depicted up here on the top, this control plane. So what's different and special, I would say, in an IP environment is because it's all standards based, because everyone's speaking the same language, ST2110, and they're all speaking the same control language, which is NMOS, that allows us to have one common control system. So the days of each individual component having their own controllers to enable routing, for instance, are gone. So you don't have to worry about, maybe I had two SDI routers that were from two different vendors. I need two control panels to operate them. That's gone now. You can expand your network as much as you want just by adding more IP switches. And guess what? Anybody's control system that speaks NMOS can now control this.
So do I have to give up my push buttons? A lot of people have grown pretty attached to those.
Yeah, absolutely. And I would say in the early painful days of IP many years ago, we didn't have the push buttons, and that's one of the reasons NMOS came into fruition was people didn't want to have to type IP addresses to connect IP equipment. So about 3 years ago, the NMOS group got together and said, how do we make this simple? How do we make it plug and play? How do we make this as easy or easier than an SDI world? So that's essentially what we did, is by creating this NMOS layer and allowing it to be programmed into our existing button panels. There's actually many manufacturers that take the exact same button panel that they use for SDI with a little code update. They can now speak NMOS and control the system. So the look and the feel is the same as it was in the SDI world.
So a lot of times when I'm reading about NMOS specs, they're talking about APIs. Do you want to kind of explain what those are?
Yeah, sure. API stands for Application Programming Interface. It's kind of a fancy software guy term to say, here's the way that two different pieces of software can communicate with each other. And what we've chosen in NMOS is really the simplest one. And it sounds really complex. It's called a RESTful API, but it's really the simplest one, which is based on HTTP, the same protocol that your web browser uses. So using HTTP, actually any computer with a web browser can read the resources in any of these devices here. And we also are able to send commands just like a web browser would to configure these. So it's really quite simple.
So would it be fair to say that a RESTful API is kind of the D-sub connector of software?
Yeah, absolutely. It's really it's a nice simple interface that is common across all components, and it's really just plug and play.
Yeah, and you don't have to worry about getting your signal and ground crossed, I guess, huh?
Yes, that's the nice thing about having a common IP interface. No more making special connectors and building your own cables, and it's all IP. It all plugs into the switch, and the software speaks a common language.
Well, that's great. So how is NMOS put together?
Well, we'll talk a little bit about how it's connected and how it works in this next example here. So I think one of the key points that I wanted to point out in the beginning is, think of it as it's a way to control this new 2110 ecosystem. And so why do I need it? Well, what we're doing is we're replacing SDI with fiber in 2110. That's essentially what we're doing. It gives us a new mechanism to talk, and we're replacing these cross-point switches with broadcast receive models. So, in the old days, we were able to just, set a cross-point, throw a switch, and then we're able to make these connections. But you were kind of limited to what you were able to do. If you wanted a bigger switch, you needed to replace this whole thing wholesale. Whereas in IP, because it's more of a broadcast receive model, you can add more switches, you can add more destinations, and this thing grows linearly. That's really one of the big benefits of IP, is this flexibility and the scalability that it brings.
Well, plus you don't have to have all your signals perfectly synchronized with each other and all in the same format. You can handle a lot of different things on one network.
Yeah, that's exactly right. Yeah, and you don't have to have 3 or 4 different blackburst signals. You don't need a, HD and an SD and a 24 frame and all that. It's a single PTP that connects them all and synchronizes them all together.
Yeah, well, that makes a lot of sense. So once I've decided I'm going with 2110, it's kind of a natural migration into NMOS. So how are NMOS systems kind of put together?
Well, I'll walk through how it works in an NMOS system. If we look at the individual components, these are very similar to the ones you saw on the first slide. So you've got your control panels in the upper left. You've got some sources down here in the lower right, or lower left, they could be cameras or video servers. And then some destinations over here on the right, could be a display, could be a production switcher. So the very first thing that happens, and this is something that doesn't happen in SDI, is all the sources register themselves with this thing that's called an RDS, or registration and discovery server. It's a really cool feature. It's what brings the plug and play. So each device announces itself. It says, hey, I'm a camera from vendor A. This is my capability. And they're all stored in this database. And then moments later, the control system can query this database, and it can see all the devices on the network. So you don't have to wonder, is SDI 7 actually plugged in to the router? Is it powered on? Because they've all announced themselves. So, and you can even do cool things like auto-populate the buttons on here with the vendor ID or the product ID that the vendor has provided. So now you've got a control system and a control panel that understands what all the components are out here. The next question is, well, how do I do a switch, right? Because there's no cross points anymore. How do you do this one of these fancy network-based switches? And the way that works is using a technology called IGMP, which stands for Internet Group Management Protocol. It's just a fancy way of saying that the controller is going to tell the destination to tell the switch to subscribe to a particular multicast stream or a video channel, if you just want to think of it from that standpoint. This monitor wants to look at camera 2. So he sends this message in this special IGMP format. And what it says is disconnect from camera 1 and connect to camera 2. And this is all inside the switch, by the way. This little cloud is the switch itself. So without any communication directly from the control panel to the switch, we're able to make these switches happen.
Well, that sounds convenient. So the end devices talk to the controller, and then the controller tells them, okay, you want to switch from camera 1 to camera 2. And of course, if somebody's wants to make that happen, they can issue a command to the system, or hopefully push a button on the control panel.
Yeah, exactly. You could either push a button, or you could send a command from a web GUI. You could even write your own software quite easily to be able to issue these commands. It's all just HTTP puts and gets.
And so the registry is not very much different than what happens when you take your laptop into a coffee shop and get on the network there. It's similar functions, right?
Yeah, absolutely. It's just a database that records the functions. So when you go into a coffee shop, you're getting your IP address from the local server that serves up your DHCP address. So in this system, so again, it provides the information that PC needs to talk to the network. So we do the same thing in NMOS. In addition to the mechanisms I've just discussed, we also have mechanisms where each device can learn about the environment it's in, like the coffee shop that you're sitting in. So we can learn what version of NMOS am I running? Is it secure or insecure? What are some of the resources that I need to connect to, like the PTP Grandmaster? What's his domain ID, so I can automatically connect to him? So we've tried to build in a lot of these things automatically so that the devices can wake up and see where they are and know what system they're in and self-configure.
Yeah, it would be kind of a nightmare if every time you went to a coffee shop, they'd have to like allocate an IP address for you, huh?
Yes, that would be very challenging.
All right. So then the gateway, that looks pretty complex.
Yeah, it looks complex because there's lots of boxes in here, but I'll walk through them and show you that's really a lot simpler than it looks. So let's say you want to build a gateway. You want to build a device that takes SDI down here in the lower right and converts it to 2110, which is a common function. There's a lot of legacy equipment out there. Well, how would you do it? Well, it's going to be a combination of hardware and software. The hardware is kind of down here on the bottom, and as I mentioned earlier, we offer cores to simplify this. And these cores provide all the 2110 functionality, and then allow the customer to actually extend that and add additional capabilities. But somebody's got to talk to the hardware and tell it what to do. Well, that's where the NMOS core comes in. So the NMOS core is just a daemon that's running under an embedded Linux operating system that's sitting and listening for commands. And he's publishing these things that are called resources, but they're essentially just like a folder structure that you would see in a web browser. So if you browsed to the IP address of this node, you would see all these subfolders under here that are devices. They're not really folders, but they look like folders. So then your ST2110 controller can send a command. It can say like switch A to B, and it does that by writing little bits of information to these different resources. The NMOS core sees that it's happened. It sends those parameters down to the 2110 core, which tells the hardware to do what it needs to do. In this case, it would be enabling the flow from SDI. It would be encapsulating it appropriately and providing all the information that it needs to create a valid 2110 stream.
That doesn't seem so bad.
No, not too bad at all. And also we have our PTP, our friendly PTP sitting over here on the right that's making sure everybody's synchronized and marching to the same beat. So
the interface spec for NMOS isn't one big monolithic document. It's broken up into a lot of different pieces. You want to talk about those a little bit? The different ISs?
Yeah, sure. There's different interface specifications. We've talked about ISO 4, which is the registration, which is everybody telling the controller who he is. We've talked about ISO 5, which is the switching, which allows you to say, I want to switch now. You can either say, you can also say, I want to switch in 5 minutes, or I want to switch at 12 o'clock noon. So that's pretty flexible. But then there's a couple others. The next one that's really interesting is ISO 7. This is event and tally. And this is, again, if you look back to the golden ages of television when we had to do these with DB25 connectors and custom cables and breakout boxes, it wasn't a lot of fun, right? Getting it all working. So what we've done, since we're moving everything to IP, of course, the control is over IP now, but we also are standardizing through NMOS how to do the event and tally, which is like GPIO over IP. So in a system like this, you'd have your production switcher, and he sends a program tally every time a camera, for instance, is selected. A tally signal is asserted for that. And following the NMOS specs, it sends it actually 2 different methods, WebSocket and MQTT, so that we've got lots of compatibility. And then the camera can then subscribe to that message, much like in the switch, the receiver can subscribe to a video essence signal. The camera can subscribe to a tally essence signal and use that to light up the nice little red light on top.
Yeah, I'm wondering when we're going to get to the point for home studios where we have to have tally systems. That'll be interesting, huh?
Yes, yes, that will. So the other IS that's kind of interesting is ISO 8. So this is audio channel mapping, which is kind of a nice thing to have. We had it in SDI. It was a little cumbersome. You had to plug a special board into your SDI router to do a de-embedding, and then you'd mix it together and then re-embed it. That's all gone away as far as the hardware for it, but the functionality still exists. By pushing it into the network and using the network topology as our switching infrastructure, and by virtue of 2110's independent transmission of audio, video, and meta, we can now do a lot of cool things. So we've got all these audio channels floating out there on the network, and video channels as well. But let's say I want to do a remapping of the audio. I don't need a special piece of hardware that decodes them all and shuffles them and puts them back out. Any receiver out there on the network that's ISO 8 enabled, and many of them are, can decide what audio channel it wants to associate with its main video channel. And it can do remapping and flipping. And for instance, this example over here, we've got 3 different video streams coming in from 3 different harmonic decoders. And each one has a different audio footprint, as you can see on the left. And what we're doing on this receiver, a 2-channel receiver, on one channel, we're actually grabbing a bunch of different random audio feeds and associating them with the video. On the second one, this bottom one, we're doing an inverse. So we're taking this harmonic top left image, inverting the audio, mapping channel 1 to channel 16 and channel 16 to channel 1. So without any extra hardware, we can do a pretty fancy audio shuffling in IP with NMOS.
And the nice thing about this is that you can do it right in the existing IP switches. You don't need even really a board for doing it, right?
Yeah, that's exactly right. The streams are all on the switch, and it's just the receiver is subscribing to the one that it wants to put it together in the particular order that it's looking for.
Yeah, boy, that does sound a lot more simple. Okay. So yeah, let's talk about switching. This you kind of got me interested in that. Now, how does this the switching process work? And there's a couple different ways of doing it, right?
Yeah, exactly. Yeah, I walked through a little bit earlier the IGMP, but just as a review, in this method, the destination is sending a message to the switch and saying, I want to subscribe to this particular stream. And that works really well. We thought at first that this wasn't going to work in very large systems because it could be a lot of traffic. But we found that up to 2,500 nodes, different devices on the network could be supported through IGMP. But because we weren't really sure in the beginning how well it was going to work, we came up with another system which is called SDN switching. SDN stands for Software Defined Networking. It's been around for a long time, but we applied it to NMOS to say, well, what if I just want to control the switch directly? I don't want to have all this traffic from my destinations. I want to send a message directly to the switch. So in order to do that, you need a common interface. So that's what ISO 6 does, is it defines a language. again, using these RESTful APIs for a switch to be able to, and a switch control system called a network controller to be able to communicate with this control panel, which is also called a broadcast controller. And then you can do whatever you want. You could have huge networks with tens of thousands of devices. You can also do some other cool things like network discovery. The SDN system can go traverse through all the switches and draw a nice little map of how your network looks.
So I would need something like this. Let's say if I was doing a remote broadcast, I had a bunch of cameras out at one location, and I wasn't bringing them all back simultaneously because I didn't have a big enough network pipe to get from that remote location back to my studio. I'd kind of have to do some switching out there as well as some switching locally, right?
Yeah, absolutely. And this could help for that. IGMP, as I said, works very well in large systems, but there are times when you need to have direct control over the switch and don't want to leave anything to chance. So we do have a provision for that. It's an optional part of the NMOS standard, but it's there in case it's needed for a particular installation.
So are there many companies making the broadcast controllers and things like that, or is that kind of um, a small market?
Yeah, it's a little bit small. So as I mentioned, the switch vendor really has to buy into this to make it work. And a couple of them did, and a couple of them did some early demos. But I think once they saw the results of the tests that thousands of nodes were handled under IGMP, they lost a little bit of interest. But you can indeed buy solutions today that work. They're just not as widely deployed as the IGMP systems.
All right, cool. So this is an IP network, right? We've got to think about security.
Yes.
Yeah, that's got to be super important. Yeah.
Yeah, and anytime you put an RJ45 connector on something, you better start worrying about security.
So how do we make it happen?
So there's a few components in this. And this is really where most of the NMOS committee activity is these days, trying to work through all the details of the secure communications and getting it all nailed down. Let me walk through an example here that might explain this a little better.
Good.
So, we've talked about some of the basic components. We know we have a broadcast controller, and we know we have an IP source, and we know we have a destination. Well, what if we want to secure it? What other pieces do we need? Well, we're going to need an authorization server. And, it's an IP world. So just think of this as a piece of software running on some PC somewhere. And he's going to make sure that only authorized users are given access to the system. So what happens is somebody logs into their broadcast controller. That's one new thing that'll change. You're not used to logging into your button panel on your SDI router, but if you want to have a secure environment, you'll have to log in if it's certainly if it's a GUI-based system, or maybe you'll have fingerprint readers on the button panels or something when you push the button. But some way you have to identify yourself, and you send this request to the authorization server. It says, "Hey, it's me. Here's my name," and it uses this protocol called OAuth, which is pretty common in web-based authentications. And the authorization server says, "Okay, yes, I know who you are. You're on my access list." So it sends back this nice little token, and the token is kind of like your get out of jail free card. It says, now this guy is authorized to do something. You use this ticket, and you can crash the gates. So the broadcast controllers, shows this ticket to the IP source and says, "Hey, look at me. I've got this golden pass. Please turn on your source and start sending it." The IP source says, "Well, wait a minute. Let me check. Let me see if you're really who you say you are." So it compares it to the public key of the authorization server, and that ensures the validity of this token. So once that's ensured, it goes, "Okay, fine. We'll turn on the stream. We'll start." So now it's blasting its 2110 stream to the switch.
Mm-hmm.
But again, it doesn't go anywhere because of IGMP. You don't want to blast every stream everywhere on your network. All source streams stop at the switch until someone is subscribed to them. So the second half of the process is the broadcast controller has to tell the IP destination, "Hey, please subscribe to that stream. Here's my golden pass." And of course, he'll validate it as well with the public key. And if it all matches up, he then accepts the stream. And now you're moving your video audio meta from point A to point B.
So is there any information in band that we need to be worried about from a security standpoint?
Potentially. So I guess you're asking is, do we need to encrypt the content itself, the
Right.
essence, the audio, the video, the meta? And we've done work with some customers that sell to military and defense. We've actually added some extensions to add that level of encryption. So doing full AES 256 encryption of the audio and the video. So it is possible. It's not, there isn't a standardized way of doing that now. Fortunately, NMOS is pretty flexible. So we did some extensions to NMOS to allow it to support that.
Mm-hmm.
And there's some activity going on in the NMOS modeling group where we're trying to standardize that so that as more of these demands come around, we'll have a standardized way of doing it. But a short answer is it's possible. It's not very common right now. The first step is let's just make sure the control is secure and that only people that are authorized can route video around a facility.
Mm-hmm. And how do you make sure that the security is working? How do you test this stuff?
Well, fortunately, this isn't new. We haven't invented anything new here. It's using standard AES cryptography. It's using standard techniques like these OAuth and JWT. So there are lots of software test suites out there that'll validate this. One of the activities we're doing in the NMOS group and working with the JTNM is creating testing programs and test suites. So JTNM is the Joint Task Force for Network Media, and it's a combination of a bunch of organizations led by EBU and IRT doing a lot of the work. There's SMPTE and others that are participating. So what they've done is they've come up with a program. It's called the JTNM Tested Program, and it's a way for vendors to be able to bring all their gear. And pre-COVID, we're actually all getting together in the same room and hooking everything up and testing it and running these batteries of test suites. And the engineers had time to tweak things if they needed. And we were able to validate, and actually everybody would get a little badge if you participated in the tests. You'd get a badge that would show what test that you participated in, and your results are published on a web page. It's a very important thing for a customer buying 2110 or NMOS equipment to make sure it's got that cute little badge on it that says JTNM tested, because that provides you assurance that you can connect vendor A and vendor B together. Not only will the 2110 streams talk, but the NMOS communication will be compatible as well.
Yeah, it's kind of like some of the fun times we went through with SDI. I mean, it was usually pretty easy to get the video to flow, but to get all the embedded metadata and things like that working was a little bit more of a stretch. Sounds
Yeah.
like we're at the same point here.
Yes, we are. It's a little easier now because it's IP based and we've got test scripts that we can run. And I mentioned we used to all get together. The last test we did virtually because we can just remotely log into other facilities and we can run these test scripts, and we don't actually all need to be in the same room to be able to test this out.
Yeah, that's great. That's great. So let's talk a little bit more about some of the other aspects of NMOS. I mean, what should people really know about it?
Yeah, well, it is the interoperable control system for our new IP world. It's a really crucial component that ties everything together. It started with ISO 4 and ISO 5. ISO 8 was added a little over a year ago, and the important thing to know is that it's not an experiment anymore. It's not a test. 3 years ago, you might have said that, but for the last couple of years, it's been out, it's been tested. There are vendors that are providing this. It's solid, it's stable, and it's something that should be seriously looked at as a really not an option, but as a required component for any IP-based system. And that's just not just my opinion, but the EBU has actually published a document. It's the minimum requirements for a interoperable IP system, and they spell it out very clearly in there. You shall have ISO 4, ISO 5, ISO 8, ISO 9, because this is what makes the transition to IP simple, which is what everybody wants. Nobody wants to be struggling to make all this work. If everybody follows the guidelines and everybody's systems are built in compliance with it and tested in compliance with it, it just makes it that much easier for the end customer.
Cool. And BCPs, you want to talk about those for a minute?
Sure, absolutely. Yeah. So BCP stands for Best Current Practice. So some of the work we do in NMOS is released as an IS, a specification, but there's other work that doesn't define a new API, a new software interface, but it's more of a guideline of how to use some of the existing APIs. So there's a couple ones. There's BCP 002, which is the grouping spec, and that's a way to form these natural groups. You might want to associate a video and an audio and a meta that all come from the same video server, for instance. Remember, they're sent as 3 different streams. So on the network, it's sometimes hard to put them together and know who came from what. So using this natural grouping and this group hint, it's a nice, easy way to say, oh, these are all from the main camera, or these are all part of my production output. It's this audio 5.1 channel stream and the video. Similarly, on the security side, we've got an IS-10, which talks about authorization, but we've also got a couple BCPs that go with it that say, well, here's how you provision a system. Here's how you use things like HTTPS in our API communications for security. Here's how you deploy certificates, for instance, for making sure that you have trusted sources. So those are all covered with these BCPs.
Yeah, so they're kind of the supporting documents. They're not really part of the official spec, but they sure help you figure things out and give you advice on how to do some other things, I take it.
Yeah, absolutely. And that's the goal, is we want to have a set of tools that we can hand over to a facility or a system integrator that gives them everything they need to quickly come up with a very powerful IP-based system.
Very good, very good. So anything else you think our audience ought to know about NMOS?
Well, I think that pretty much summarizes it. It gives us everything that we had in SDI, plus some magic, like with the audio routing that we mentioned, and plus some magic of identification of sources. It brings a sorely needed security layer, which there just wasn't a practical way to do in SDI. And NMOS is the glue that holds all this together and makes it possible to create these interoperable systems, which in the end allow extraction of business value for our customers.
Yeah, I really like that interoperable part. It used to be you had to buy a certain controller for a certain cross-point switch, and not everything would work together, or you had to buy everything from one manufacturer. But this openness really does make a difference, doesn't it?
Yeah, it's huge. It takes a lot of the risk out of it, and you know that you can expand and connect different components together and not worry about having to be in a single vendor ecosystem. It allows you to get the best of everything, just like when we used to buy audio components separately. You'd buy the best tuner and the best amplifier, the best turntable. Nobody wanted to buy everything in the system because no one vendor can provide the best of everything. So it's really powerful and enabling for our production customers.
Very good. Well, Jed, thank you. Thanks for your time today. Been pretty informative. I see you put your contact info up there. So people can contact you to see how this stuff actually works.
Yep. Please feel free to reach out to us. If you just want advice on building your system or building your product, let us know. We've also got demonstrations that we can do virtually. We've got an entire 2110 and NMOS system set up here with PTP, and we can walk you through it. We can show you how it all works, and we can show you how our hardware and software cores can enable your products to have industry tested functionality and reliability, and provide you very fast time to market.
Great. Thanks so much. I really appreciate your time.
Thank you, Wes. Have a great day.
You too.